My name is Vaibhav Pathak, and I would like to thank seminar organizers to giving me this wonderful opportunity to present my work. So my topic is like second order QCD correction to semi-inclusive deep inelastic scattering. And so basically we work on strong forces, and we try to study its feature, and which is also responsible for the binding of nucleons inside the nuclei. And it is very different from the electromagnetic force, which is like electromagnetic interaction is the interaction between the charged particle, and here we have something called color charge, and this QCD is the interaction between the interaction between color charges. So first of all, if you want to know, like we want to discuss about some hadron. Hadron means hadrons are the composite particle, and if you want to understand something in general composite particle, so you should best way and easiest way is to break it. And what is the constituent of that composite particle is to first we will break and we will study that. So that's what scattering do. We will try to understand its structure by scatter some electron or proton or hadron, something like that. And so precision physics, so we call what we do is perturbative precision physics, and it is important because it gives a very give details about proton and neutron structure or any hadron structure, and it will give a check if there is any new particle in the nature that we haven't found out. So it is basically also give check for the beyond standard model physics also. So if you want to, why electron ion collider is necessary, why it is necessary for us. So first of all, like if you want to, electron we are using here in electron ion collider because electron doesn't have any internal structure. So if you want to collide, if you want to get the structure of composite particle, so you best way is to collide with some fundamental particle which itself doesn't have any internal structure. Otherwise it will after scattering your result will get messed up, and you so fundamental particle if you use, the final state result will only tell about what is the structure of your composite particle, or you can say hadrons. So okay, the burning question for these main question for this electron ion collider would be like how nucleons acquire mass. In the basic physics we know that, okay, so the sum of the proton and neutron mass is always greater than the mass of the atomic mass. It is because that the sum of the mass will get into binding energy, and it will be atomic mass will be always less than. But in QCD it is totally opposite, because if you see that what we found that the mass of the quark, which is very light mass, quark are very light, and gluon which are massless nearly. So if you add all the masses of the quark and gluon, they only give the 1% of the mass of nucleon. So how these nucleons, or you can say proton, is getting 99% mass? And now next question would be like, okay, so spin of the proton, let's say spin of the proton, one would think that okay, spin of the proton would be like the spin of its constituent, but what we found that the spin of the proton spin of the quarks and gluon only contribute to 40 to 50% to the spin of the nucleon. So we need to further probe about this. And what is the gluon saturation and color glass condensate? So we found that like when you increase the energy of the nucleon, the gluon number density also increases. So any theory about this quark gluon interaction will predict about this. But this theory also put a cap on how much gluon number density can increase. So we found that after certain point gluon number density gets saturated, and in this regime we expect that there is a gluon matter condensate formed, and we call as color glass condensate. So to know about these things, it is also we need to know more about these things. So what is the structure and how it is behaving at high energies, and also quark confinement. So we found that at high energy, like inside the hadron, quarks are moving very freely around it, very freely inside the hadron, but they cannot come outside the hadron. So we need to study more about this quark confinement, and many more questions it will address, but these are the main questions. Okay, so we use a parton model, which is given by Galban and Bjorken, and it is the model at a very high energy limit, or you can say infinite momenta limit, where the hadron is Lorentz contracted in the direction of collision, and interaction between their constituent get time dilated. So okay, what are the assumption of the model? You have to assume that, like they assume that the incoming particle is coming with very high momenta, and it is seeing hadron as a collection of point-like particles which are held together by mutual interaction. And what is time dilation? You can think of time dilation is like the interaction between electron and the parton. Parton are the constituent of hadron. Is a time scale is very shorter in compared to the two constituent itself inside the hadron. And this model also says that, like cross section you will find with the let's say electron with that hadron is equal to the sum of the cross section of individual point like particle with incoming particle. So what is theoretical preliminary? So first I will tell you what is inclusive, since my work is semi-inclusive deep inelastic scattering. What is inclusive deep inelastic scattering? Where in deep inelastic scattering we take a hadron and we collide with electron, and in the final state there will be bunch of particle, and we will integrate over all the particles, and that's why its name is inclusive. Inclusive means in integrating over all the hadron, all the particle out final state particle. And that's how with the help of final state we try to probe what is the internal structure of that hadron. But in semi-inclusive deep inelastic scattering we go one step further ahead. So in that step electron is colliding with hadron, and many particles is coming out, and one of the particle in the final state is again hadronizing. Now in the DIS deep inelastic scattering you had only one particle in the one hadron in the initial state. In the semi-inclusive deep inelastic scattering you have one hadron in the final state and one hadron in the initial state. So this is our process, and we calculated this at the partonic level, this part. So we calculated this part, and where we have assumed that quark is massless in the initial and final state, and this gluon is having energy minus q square. And now so we need to calculate this capital W mu nu. But since hadron is a composite particle, we cannot directly jump into it and calculate this part. So for that we always calculate this thing. This is partonic tensor, or you can say it is way for parton cross section. So we will calculate this part, parton cross section, and this capital W mu nu or smaller w mu nu are related with this relation, where f is called parton distribution function and d is called fragmentation function. F is actually probability of getting a parton out of hadron, and d is the probability of getting out of hadron from a parton in the final state. So yeah, these are the processes which are relevant for our cross sections. So at leading order we have only quark going to and this is our final state particle which is going to hadronize. And next leading order, similarly we have all the processes which are initiated with quark and gluon, and one of these final state particle need to be hadronized, and all the other particle in the final state we will just integrate over there. So these are the okay. So processes with only loop, we will call them as virtual processes. Processes with one loop and one emission, we call them as real and virtual process, because one real, one virtual. And processes with double real is we call as real processes. Okay, these are the processes, and any of the final states can hadronize. I have put only H to one particle, but you can put anywhere H, that any particle can hadronize. So by use of form and Mathematica, and we calculated these all the processes relevant for the second order. So once you calculate all your cross section, you will find that there is a UV divergence and IR divergence will be there. So for the UV means ultraviolet, IR means infrared. So for UV, to remove the UV divergence, so this is a divergence is coming from when you take energy very high. So you can remove this divergence using coupling constant, and for IR coupling constant renormalization. So there is one, now you will have only IR divergences. So Kellen theorem states that if you add all the diagrams and integrate over all the initial and final state, you will not get any, your infrared remaining singularity will get cancelled out. So this is for any order, you will have soft coming from virtual diagram, soft collinear coming from virtual diagrams, and similarly for real coming from virtual diagram, collinear coming from virtual diagram. So once you add all the diagrams, soft coming from soft divergences coming from virtual diagram and soft divergences coming from real diagram will get exactly cancelled out. But since you are not integrating over initial or final state, you are only integrating over final state, but except one particle which is hadronizing. So you will have collinear singularity in both in initial and final state. So collinear singularity will not get cancelled out, and this will be your expression of. Now one thing we use is called to remove initial state and final state singularity, collinear singularity, we use called mass factorization. And using what we do in mass factorization, we take our cross section and we factorize into three parts. So this is gamma, delta gamma. This is our total completely finite part that we want. This is our cross section that we want. We will factorize our cross section into these three things. Gamma will be totally divergent. Gamma tilde will be totally divergent. Basically what we did, divergences of sigma we dumped into gamma and gamma tilde. And now I have already mentioned in the initial slides what are F and D. What we basically do, the divergences coming in the gamma be absorbed into F, and the divergences coming from gamma tilde be absorbed into D. Now you will have only delta, and which is completely finite, and this is what you want. And what is the future direction? So we basically plan to calculate a polarized cross section and many other processes where we have used gamma. Now in the initial slide I have showed you intermediate particle as gamma, photon. Now one can use Z particle, and we are planning to use Z or W or many more. So that is called parity bulleting. And now, so our goal is to provide better data for EIC to get more understanding what is the hadron structure, and obviously if we get better understanding what will be the interaction between partons, that we will get to know. Thank you all. Okay.
What will happen if you put in W these D bosons? They are massive propagators. So how
do you
deal with that?
So here, if we put here, we are planning to, we haven't started it, but we are planning to put W here, and we will consider this parity violating factor, and mass will be also there.
So how do you deal with the propagators there if you have mass?
So
something also massless case.
No. That won't be remain massless case, because here.
Yeah. Now you have to put in masses.
Yeah, here, na.
Yeah.
So that we
So
need
it will
to
be
see
more
it.
difficult.
It will be, yeah, obviously it will be more difficult than this.
Any more questions? Okay, let's thank the speaker again.
Oh, thank you.